Okay. I had you pick up a second sheet of notes today because someone was asking a few questions on the review packets for tomorrow's quiz that made me think we could use a little separate instruction on how piecewise functions work. The book doesn't have a separate section on piecewise function. It kind of mixes it into everything. But we talked about continuity with piecewise functions back when we were doing limits and continuity, but now that we're doing differentiability, we have to look at whether or not a piecewise function is differentiable. So, in this first example, the breaking point is at 2. So, if we're approaching 2 from the left, we're approaching it with some slope, whatever the slope of x squared is at 2. And if we're approaching 2 from the right, we're approaching it with whatever the slope of this line is at 2. So to look at differentiability, we want to look at what is the derivative, what is the slope coming in from the left, what is the slope coming in from the right, and seeing if they're equal. Okay? So our derivative coming in from the left, our derivative is 2x. So specifically at 2, that would be 4. But coming at it from the right, our derivative is what? What's our derivative of this equation? No, negative 2. The derivative is negative 2. And so when you evaluate that at 2, you still get negative 2. That's a constant derivative, so it doesn't really matter. So what we find is the slope coming in from the left does not equal the slope coming in from the right, and therefore this is not differentiable. At 2. She did, yeah. Are you Natalie? Yep. I'm going to sit right back there and take it. There you go. Yeah. So I'm going to, like normal, I want to give you some insight as to what we just did there. So let's do this. I need a different angle. If I graph x squared and 8 minus 2x, and we're really interested in what's happening at 2. So if I set my window from 0 to 4, 2 will be right in the middle. And I'm just going to try to find the right y window. Negative 20 to 20. Okay, so here's our break in action at 2. Prior to 2, we're following this curve, which is part of the x squared curve, and then beyond 2, we're following this line. So what I'll do for you up here is kind of trace over this. Here's our piecewise function. Leading into 2, we're there. Coming out of 2, we're there. So it's a continuous function. We can all agree on that. You're just looking at the blue. It's a continuous function at 2, no break in action, but it lacks differentiability because it comes to a sharp point. In other words, the slope changes drastically. The slope is, progressively changing on this parabola, and once we get right to that instantaneous point on the parabola, the slope would have been, what did we say, 4? Did we say 4 when we differentiated from the left? But then immediately after 2, or starting kind of where this one leaves off, this line always has a slope of negative 2. So the slope goes from 4 to negative 2 at a sharp point. There's no progression leading one into the other. So we're not differentiable. Does that make sense? Okay. The next example is going to be a little bit different, a little bit of a different spin on it. But we can start doing the same thing. So if I find the derivative, our breaking point is at 3. If I find the derivative coming from the left, the derivative is 2x. So when I evaluate that at 3, I get 6. Coming at 3 from the right, my derivative is also 2x. So when I evaluate my slope at 3, I also get 6. So what's your thought here? So Taylor's saying, well, it should be differentiable because they're equal, but Serena is saying no because she's onto the point of this question, I think, probably. Why is it not? Because it's not continuous. So if we take a look at, and don't worry, Taylor, I kind of set you up for that. Yeah. You fell for it. So if I zoom 6, and then I'm really curious as to what's happening at 3, so I want to change my window here. So coming from the left of 3, I'm following this graph to here. There's where 3 is. And then to the right of 3, I jump down and I'm following this graph. So again, it's going to be more helpful if I trace over this. Here's 3. Coming from the left of 3, that's my graph. To the right of 3, that's my graph. So that's my piecewise function. I'm going to take this out of the way because that's easier to kind of look at. There's my piecewise function. Yes, the slope as I approach from the left right here is 6 going into 3. And yes, my slope coming out of 3 is also 6. But if you lack continuity, then you cannot be differentiable. It's just not even on the table. Okay, so the first criteria for something being differentiable is that, number one, it has to be continuous. And then, if it's continuous, it may or may not be differentiable depending on the slope changing. So even though I kind of just calculated the slope in the last one, that was enough for the first example, okay, because the slopes weren't the same, so it was not differentiable. We never really checked for continuity there, although when we graphed the picture, we saw that it was. But with this one, algebraically, you check for continuity as well. In fact, that should be the first thing that you're doing. So to check for continuity at 3, we just plug in 3 to both of them to see if the end point of the first piece is the same as the starting point for the second piece. So when I plug in 3 and just do f of 3, I get 14. If I'm coming at 3, I guess, from the left. But if I'm coming at 3 from the right and plug into the second piece, 9 minus 7 is 2. And so because one ends at 3:14 and the other one picks up at 3:2, we lack continuity and therefore we lack differentiability. Okay? So underneath this, and Jacob, can you go erase that for me, please? I'm going to write really what the general test is to evaluate differentiability. On a piecewise function. Number 1, you really should test for continuity first. So test continuity first. And for that, you just need to plug the point of interest into both pieces and see if it's the same. That'll give you your limit coming from the left, technically, and your limit coming from the right, technically, and if they're the same as the actual function value right there. So that's, I'll put that in parentheses, the limit as you approach whatever c value from the right has to equal your limit as you approach whatever c value from the left has to equal f of c, not f of x. And if you're continuous, great. Then we also need to check differentiability, which the notation here is a little less mainstream, like that's very mainstream. But if we're testing for differentiability, you want, and again, this is my own notation, but I think you'll know what I mean by it. You want f prime at c coming from the right to equal f prime of c coming from the left. That's not mainstream notation, that's just Rahill notation. But do you know what I mean by that? Check your derivative from the right. So up here, that was the derivative of this one. And check your derivative from the left. So that would be that one. And see if they're equal. And if they're equal, then it's differentiable. Okay? Any questions? All right. So the last one, so in this one I got something that was continuous but not differentiable. And this one I got something that looked like it was differentiable but it wasn't continuous, so it couldn't be differentiable. And now I was trying to come up with an equation or a piecewise function that would do both. And then I decided, well, I'm trying to write this problem. I thought, well, that would be an okay enough exercise for you guys to do. So I left this b value for us to find on our own. In order to be differentiable, and I'm going to try to find b to make this thing differentiable, I first have to be continuous. Okay, so I first need to find the b value that will make it continuous. And then I'll be able to evaluate whether or not it's also differentiable. So in order to be continuous, my limit coming from the left, which would be plugging 3 into here, f of 3 is 9 plus 5, 14. So the function value coming from the left has to equal the function value coming from the right. Now, coming from the right, when I plug in 3, I'm going to get 18 plus b. And these need to be equal. F of 3 coming from the left and f of 3 coming from the right. And so what would b need to be if these two need to be equal? -4. Okay? So in order to even have a chance at being differentiable, they have to be continuous. So we found that b would have to be -4. Okay? Now to be differentiable, and now to see whether or not it is, because there's no other variable to find here, to see whether or not it's a differentiable thing, I'm going to find the derivative coming from the left, which is 2x, and then I'm going to evaluate that derivative at 3 and get 6. And I'll do the same for the second function coming at 3 from the right. So the derivative of 6x minus 4 is just 6. And so when I evaluate that at 3, of course, since the derivative is constant, that's also constant. And they equal, and they were continuous. We made it so that they were continuous. We found the b value to make that happen. And so in this case, this is one of the rare cases where a piecewise function is differentiable at 3. So f of x is differentiable at x equals 3. And one more time, I'm going to show you this graph so you can see it. So what happens at 3 here is that this kind of comes up. We're following this to the left of 3. And then once we get to 3, we start following this line. And you'll see it better if I draw over it here. So here's 3. So to the left of 3, we're here. And to the right of 3, we're here on that line. So what just so happens is that Coming into 3, my slope is 6. Coming out of 3, my slope is 6. So it's just the perfect point so that it's progressively 6 right through that point, and you don't have a sharp corner. They kind of melted into each other a little bit. Does that make sense? Elliot, what's Aiden's doing? Elliot was smirking, looking at Aiden. I look at Aiden, and he just grins at me. And then I look back, and now he's in full laughter. Huh. You little snake. All right, so there's my little side lesson on piecewise functions. That's just a side lesson. And I just dreamt this up this morning, first period, so I threw that together because I think we needed it. It will help you on some of those review questions on that packet to help prep for tomorrow's quiz. Today is nothing more than just a closer look at product rule, quotient rule, and options that you now have moving forward. Because you have the power rule, and now you have these product quotient rules, and oftentimes problems can be done in either way. Okay? So if we look at this first example, the instructions say to do it without using the quotient rule. So kind of the way we would do it on day 1, which is to first rewrite it. Thank you, Dominic. You're welcome. And then once you're done with that, say nothing. When I go to differentiate this, I'm going to use the power rule. What do you say?
This is being recorded right now.
I know, you're right. Yeah, watch what you say. So once I've rewritten it, I'm just going to now differentiate it by using the power rule. So my 2 is going to come out in front. That 5/4 is going to turn into 10/4 x. The derivative of negative 3/4 is 0. So this will simplify to just 5/2x. Have a great vacation. He's lying. Because you're doing AP questions right now. That's why they're hard. These are AP test questions.
Why is there 5 choices?
That's the AP test.
That's awful.
I know. All right, so what I'm going to illustrate for you now here is that even though it told us to do it without using the quotient rule, I'm also going to do it using the quotient rule. So our bottom times what's the derivative of the top, Anthony? 10x, very good. Minus the top times the derivative of the bottom. What's the derivative of the bottom, Hannah? 0. 0. All over the bottom squared will be 16. So the nice part about that is the 0 cancels this whole term. And I just have 40x over 16, which reduces to 5/2. So what I'm illustrating here is that with that type of problem, and with a lot of the type of problems we're going to look at today, you have options. If you like doing this better and just sticking with all power rule, then do it that way. If you like the quotient rule, then do it that way. You should get the same thing. Now, on something like this, I don't know that one's easier than the other. They're both probably equally as difficult. But there are going to be some where the power rule method is way too much work, or not possible, or vice versa, where the quotient rule or the product rule is going to be way too difficult. Okay? The product and quotient rule won't ever not be possible, but it may be really ugly where you don't want to do it and you want to avoid it. So like this one, for example. If you initially look at this, what are you thinking? Serena, what'd you say? Not fun. Not fun? Are you thinking you would get a common denominator? Okay, don't do this. But No, but this is what we're learning, is how to find out that, wait a minute, this isn't really efficient. So watch what's going to happen when I do that. I'm going to get x plus 1 minus 2 up top, which is going to be x minus 1 over x plus 1. That doesn't look so bad. But then if you're going to start this problem, you're going to do the product rule, and you're going to do the first times the derivative of the second. Well, the derivative of the second is going to require quite the detour. You're going to have to do the quotient rule just within that part. So you're going to have to do bottom times derivative of the top minus top times derivative of bottom all over bottom squared, just in that set of parentheses. And then you're going to have to remind yourself, where was I in terms of the product rule? First times derivative of the second plus the second times the derivative of the first, which isn't so bad. And then the cleanup, because of this, is just going to be crazy. Okay? So it's an option. It will work. It's not going to be the most efficient. What would be more efficient?
Giving up.
I have to keep it appropriate too, unfortunately. Just kidding. Minus 2x to the 4th over x plus 1. Distributing. Because now, even though I'm still going to have to do a quotient rule, it's not the quotient rule within the product rule. I would avoid that at all costs, having to do the product rule within the quotient or vice versa. Now I can just go ahead and find the derivative. I get 4x cubed for the first term. And like I said, yes, this is the quotient rule, but it's not within a larger rule. So I would do my bottom times the derivative of the top, 8x cubed, minus the top times the derivative of the bottom, all over bottom squared. And then just like things on last night's homework, the cleanup isn't going to be pretty, but I can assure you that this is a lot prettier than what it would have looked like had we done it the other way. I'm going to multiply this out. I get 8x to the 4th plus 8x cubed minus 2x to the 4th. I can combine like terms up here. 8x to the 4th minus 2x to the 4th is 6x to the 4th. And again, now depending on what your answers look like or what you might need to manipulate it further. Worst case scenario, I think you might have to get a common denominator, which would be pretty gross, but not terrible. You could do that fine, but you just have to kind of play it by ear. If it's open response, I'm fine with that. If you have to evaluate that at 3, just plug 3 in. I'm fine with that. But if it's multiple choice or you're trying to aim for that answer in the back of the book, you're going to have to manipulate. And that's not calculus, that's algebra. Okay? How do you feel about this one? What should we do? It looks easy? What would you do? Scott? Foil. Okay, so if you just first FOIL this, it's going to be x to the 4th minus 2x squared plus 1. And that is pretty easy to take the derivative of, right? Okay, that's one option. You may also do this. It's not going to be as efficient. But if you literally expand it and multiply that binomial times itself, you could do the product rule there, right? But that's going to be much longer. This one we're pretty much done. We can just derive. If we do the product rule, first times, that's going to be a longer process.
Why they showed it other version?
I'm just, because some people that was their first instinct. And just to show that yes, it will work, but it's going to be longer. And again, the more you see, and unfortunately, the more you choose the wrong method and it becomes super ugly, and you learn from that mistake, the better off you're going to be initially picking the best way. You'll start to get kind of a good instinct as to what the best approach is. Okay? These two at the bottom, pretty straightforward. They're just kind of bringing an application to it. So writing the equation of any tangent line, we need a point, which on the first one we already have a point. And we need a slope, which is going to be where we're going to derive. Specifically, we need the slope where here? At 0. So we're going to have to find f prime of 0, but before we do that, we have to find f prime of x. And again, with this one, we can do the product rule right away if we want, or we can distribute and do the power rule. But once you have your derivative rule evaluated at 0, that's going to be your slope. Your point and your slope is going to help you write your tangent line. We're not going to do that out, but we've done several problems like that, so nothing new. Okay? Flip to the back. And we're going to talk strategies here. So on this one, same old, we could do the product rule, first and second, or we could distribute and we can just do the power rule. Either or will work. Okay? This one, I definitely do not recommend the product rule, because if you do the first times the derivative of the second is going to have multiple quotient rules within it, and that's not desirable. So instead I would distribute. You get 2x squared over x minus x squared over x plus 1, and that first term simplifies even further to 2x. Now your derivative is much easier. Derivative of 2x is 2 minus, and this second part is going to require the quotient rule, but again, the quotient rule alone is a lot better than the quotient rule within the product rule. Okay? The third one here, we don't have a product rule for 3 factors. So that we can't even approach that concept. So you have no choice but to at least multiply out the first 2. In which case we would have x to the 4th plus x squared minus x cubed minus x. Then you can either do the product rule, or you can multiply everything out and get it to be one big long polynomial, and just do that distributing once, and then just the power rule. Okay? And the last one, definitely a quotient rule. But because c is a constant, your derivatives aren't going to be that bad, because your derivative of the top will just be minus 2x, because the derivative of any constant is 0, and the derivative of the bottom will just be 2x. So that one won't be bad. Your homework's there at the bottom. Quit tomorrow. Work on those packets. Don't listen to Dominic, he's lying.
Tom doesn't lie.